Hello, this is section 5.2, Exponents in Scientific Notation. Part 1, Exponents. Definition 1. Exponents describe repeated multiplication. For example, 2 to the 5th means repeatedly multiplying 2 by itself 5 times, or 2 times 2 times 2 times 2 times 2, which is 32, not 10. So the biggest mistake is that people just hear the word multiplying and they go 2 times 5 is 10. No, it means 2 times 2 5 times, which is 32. The number which is being repeatedly multiplied is called the base. The number indicating the repeats is called the power or exponent. In the previous example, 2 is the base and 5 is the exponent. Properties of exponents. Let a and b be real numbers with b not equal to 0 and m and n be whole numbers. We have the following properties pertaining to exponents. A to the m times a to the n is a to the m plus n. A to the m divided by a to the n is a to the m minus n. And we call these the same base. Laws, since the factors have the same base. We also have the property that a to the m times b to the m is just a times b to the m. And a to the m divided by b to the m becomes a divided by b to the m. And we call these the same power. Laws, since the factors have the same power. Now, a lot of times with these ones, though, we are going to be going in this direction, in which case these are sometimes called the distributive laws. Now, the reason why they're called the distributive laws, if we go from the right to left, it's like you're distributing the m to the a and then the m to the b, and that's how we get what's on the left here. Same here, distributing the m to the a or the m to the b, and that's what you get on the left here. Next one, a to the m to the n is a to the m times n. We call this the power to a power. Law, since it involves a pair of exponents. Then finally, we have a to the 0 power is 1, except when a is equal to 0, then it is undefined. And a to the 1 always equals a. We call these the null and identity property of exponents, respectively. Example 2. Simplify the following expressions using property of exponents. So this first one, x squared times y to the 0 times z squared, well, y to the 0 is 1 by definition. So this becomes x squared z squared. And if needed, we could rewrite this as xz squared using our same power laws. Next, x cubed y to the 5th over xy squared. Well, the x's have the same base and the y's have the same base, so I can use my same base laws. And when you're dividing same bases, you subtract exponents. So this becomes x to the 3 minus 1 times y to the 5 minus 2, which is x squared y cubed. Next, we have 2x squared y cubed over z squared, the entire fraction, squared. So I'm going to use my distributive law first so that this becomes 2 squared, x squared squared, y cubed squared, all over z squared squared. And then I'm going to use my power to a power law to simplify these a little further. Well, 2 squared is just 4, x squared squared is x to the 4th, y cubed squared is y to the 6th, and z squared squared is z to the 4th. And that's as simple as we can make that one. And finally, 10k to the 4th cubed times 5k to the 6th squared. So the first thing we're going to do is use the distributive laws. So this becomes 10 cubed times k to the 4th cubed times 5 squared times k to the 6th squared, which becomes 1000 k to the 12th times 25 k to the 12th, because using the power to the power rule. And last but not least, same base rule, I add the exponents, so we get 25,000 k to the 24th. Part 3, negative exponents. To extend to negative exponents, we require one new rule for any non-zero real number a. A to the negative 1 is the same thing as a 1 over a, I mean. In words, evaluating the negative in the exponent means to replace the base with its reciprocal. This extends to whatever base we have, even fractions. For example, a over b to the negative 1 becomes b over a. When our exponent is a different negative integer, say negative n, we evaluate the negative first, then apply the n. So a to the negative n is the same thing as a to the negative 1 to the n, which we know a to the negative 1 is 1 over a. Well, this will just become 1 over a to the n. And then this will become b to the n over a to the n. Note that all our properties from the previous section, for example, same base, same power, and power to power laws, still apply when dealing with negative exponents. Example 3. Use properties of exponents to simplify the following expressions. Write your final answers with positive exponents only, i.e., evaluate all negative in exponents. So we have x cubed times x to the negative second first. Well, I'm going to use my same base laws to add the exponents. So that's x to the 3 plus negative 2, which is x to the first, which is just x. Then I have x squared y cubed all to the negative third power. I'm going to do the negative exponent rule first. This becomes 1 over x squared y cubed cubed. Then I'm going to use my distributive law, so this becomes 1 over x squared cubed y cubed cubed, which then becomes 1 over x to the 6th, y to the 9th. Then we have 1 over xy to the negative 2. I'm going to take care of the negative exponent first, so that becomes xy to the positive 2. And then I'll use the distributive property to get x squared, y squared. And finally, we have x to the 5th over x to the negative 8th. And I'm going to use the same base laws. So I subtract my exponents. That becomes x to the 5 minus negative 8, which is x to the 5 plus 8, which is x to the 13. Part 4, Scientific Notation. Exponents provide an efficient way of writing and computing with very large and very small numbers. Numbers in scientific notation are of the form c times 10 to the n, where c is between 1 and 10. It can equal 1, but it cannot equal 10. In other words, this is saying c is a number with one number to the left of the decimal point, and n is an integer. A positive n indicates that the number in scientific notation is large, and a negative n indicates that the number in scientific notation is small. Example 4. Write each number in scientific notation. Count decimal places. So again, in scientific notation, I want one non-zero number to the left of the decimal point. So since my decimal point is here right now, I want it to be right here, right after the 6. I just count my decimal places. So that's 1, 2, 3, 4, 5. So this becomes 6.84 times 10 to the 5th. Now I have to determine, is that a positive 5 or a negative 5? And what I ask myself, is the number I started out with small or large? The number I started out with is small, so it's going to be a negative 5. Okay. Second one, we have 937,200,000. So when you don't see a decimal place, remember that it is right at the end of the number. We just don't write it. And this time, I want the decimal place to go next to the 9. So counting the number of decimal places, we get 1, 2, 3, 4, 5, 6, 7, 8. So this becomes 9.372. And now this is the benefit of using scientific notation. I don't have to write all those zeros out. I just have to write 9.372 times 10 to the 8th. And again, is it negative or positive? Well, since 937 million is a large number, it is going to be positive. Example 5. Write each number in decimal notation. Count the decimal places. Well, here I have 4.4836 times 10 to the third. So the 10 to the third means I have to move the decimal 3 places. Now, I always get my left and rights mixed up. So when my teachers told me, oh, when it's positive, you move to the right, and when it's negative, you move to the left, I always got it mixed up. So what I say instead, is it positive or negative? Well, it's positive, which means the number has to be large. So which way do you have to move the decimal in order to make the number larger? So to make the number larger, I need to go this way. 1, 2, 3. So our answer is 4,483.6. And now similarly with part 2, when I have 1.81 times 10 to the negative 6, because it's negative, which way do I move the decimal to make it a smaller number? Well, that would be in this way. 1, 2, 3, 4, 5, 6. And all these blanks that I went through become zeros. So this is 0.000000181. Example 6. Use a combination of regular arithmetic, algebraic, and exponent properties to evaluate each expression. Write your answer in decimal form. So another nice thing about scientific notation is it makes it easier to multiply and divide these types of numbers. Because what we can do is this will just become 2 times 3.4 and 10 to the ninth times 10 to the negative fourth, because order of multiplication does not matter. 2 times 3.4 is 6.8. 10 to the ninth times 10 to the negative fourth is 10 to the fifth. So there is our answer. When dealing with fractions, it is the same way. This is going to become 3.6 over 6 times 10 to the 12th over 10 to the 5th. So that becomes 0.6 times 10 to the 7th. But this gives us a good practice because this is not proper notation because it is less than 1. So what I have to do is I have to actually convert 0.6 to scientific notation. So the decimal is here. I want it to go here. So it's 6 times 10 to the first power. And was 0.6 considered a small number or a large number? I consider it a small number, so that's negative 1. And then I can combine that with the times 10 to the seventh. So our final answer is 6 times 10 to the sixth. And that is it for section 5.2.